Alright, in this video we're going to talk about imaginary numbers. And let's find out, well, first of all, let's start with the domain. We'll pretend that's a circle. This is the domain of all numbers. And we can divide it in half and put the reals on one side and imaginary numbers on the other. Real numbers, just by way of review, if we do a number line here and 0, they all live on this number line. And these numbers include, these are negative numbers, these are positive. These numbers include whole numbers, decimal numbers, irrational numbers like pi, e, and the square root of 2. Rational just means they can be expressed as fractions, so we'll put fractions up here. All these types of numbers are real numbers, and they all live on this number line. And the one thing I want you to get from this little illustration is that this number line is one-dimensional. We go forward and back in the same plane, that's all we can do. That can become important, maybe. All right. The lowercase I is used as a symbol for imaginary numbers, and also with that is lowercase j, especially in electronics, since I is oftentimes used for current. And in math symbols, this means the square root of -1. Now, you can't take the square root of -1 because the result is not in the domain of real numbers. There's no real number that can be squared and give us a -1. So you can't undo a -1. That's essentially what that means. And if you try and do it on a calculator, I'll pop one up here. Let's put in 1, make it negative, try and do the square root. We get an invalid input. The square root function does not understand -1. Okay, and you can do that on your own calculator. If you have a graphing calculator, it might be sophisticated enough to actually say domain error, but if you do it on any other calculator, you just get some kind of an error. Okay, and one place where those are used in electronics, amateur radio, think about an antenna system. You know that an antenna system has elements of resistance, inductance, and capacitance. And in a DC circuit, these are all in the real number system. However, if we alternate the signal, like you would get with a phone or some other use, we have an alternating signal going through here. Resistance is always in the real number system. However, when an alternating signal goes through an inductor or a capacitor, it behaves differently. The voltage will separate from the current, and we get a leading or lagging signal. You can do this on an oscilloscope and see where the voltage and the current, you need a current probe, separate, and you get a phase difference. And in order to illustrate the phase or model that phase mathematically, you need an imaginary number. So typically what you see then, especially in amateur radio, but anywhere, is a complex number. Complex does not mean complicated. We use the word in English language synonymous with complicated, but complex really means of two parts, especially in mathematics. So we have a real part. Let's say we have a resistance of 30 ohms, and we have an inductive and or capacitive reactance of 3 ohms, but it's in the realm or domain of imaginary. So a complex number has a real part and an imaginary part, and you can add, subtract, multiply, and divide those. Take a course in college algebra to learn how to do that. It's not difficult. Okay, so We've talked about real numbers and one occurrence of where imaginary numbers come up, but this is not easy to visualize. Let's take a look at a case where maybe we can visualize it a little easier. And to do that, we want to graph a quadratic equation. So we'll draw a set of axes. We're in the rectangular coordinate system here. We have an x-axis and a y-axis, and in reality these axes are number lines. So, and a quadratic has the form of ax squared plus bx plus c equal 0. And if you solve this equation for x, which has already been done for you, you get the quadratic formula. X is equal to negative b plus or minus the square root of b squared minus 4ac, and this is all over 2a. Notice the plus minus here. That's because any square, Gauss proved a couple of hundred years ago that variables to a power greater than 1 will have roots equal to what the integer power is. Roots are the same as solutions. And a quadratic draws a graph, if it's a positive, draws like the top of a wine glass, something like that. If it were negative, it would be upside down. Okay. So there are two solutions, and we can see that graphically. Let's graph the equation x squared minus 2 equals 0. And we could solve that and get numeric values by running it through the quadratic equation here. A, B, and C are just whatever the coefficients are to x. Notice there's no b term here. Okay. Anyway, we would find out if we did that, that down here at minus 2 on the y-axis, our quadratic comes down here, and it should just touch that. Okay, but that's not what's important. The important part here is that the solution is here and here, where the graph crosses the x-axis, because that's where y is 0. We've set y equal to 0 here in our equation. These are the solutions. There are two. X is the number line, so we expect the solutions to be in the real number system. Great. Okay, let's do another graph here. And let's graph a similar equation, x squared plus 2 equals 0. And again, we could run it through the quadratic formula and find out what it is numerically, but the answers are going to look funny. And if we were just to plot this, and you can plot any graphic like this by creating a table of x and y, and create some x values here, and you'll get corresponding y. And if we were to do that with this equation, we would see that where y is plus 2, we would get this is plus 2, we would get the vertex. So if we graph this, it would look something like this. And of course, it would touch the mark there. But wait a minute. We determined, and Gauss said that we have a number of solutions as to the power, but this graph does not cross the x-axis, which is the number line. Yes, it has two solutions to it, and you can find out what those are by using the quadratic formula, but they're not in the real number system. This does not cross the x-axis, which is the number line. The solutions to this are in the domain of negative numbers. Now, I want you to go out to YouTube, get online, go out to YouTube, and search on Welch Labs. And look at the playlist. You'll find in the playlist a list of 15 short little videos he does on imaginary numbers. And the very first video shows you a really neat graphic. I don't know how he did it, or I'd copy it here. He shows you a real neat graphic of why this is true, what really happens here. It turns out that, yes, it does cross the x-axis, but the x-axis is no longer in the domain of real numbers. It's in the domain of imaginary numbers. So it does cross it, but it's not in the domain of real numbers. Real interesting. Sort of indicates to me that when we're talking about imaginary numbers, we are now talking about a two-dimensional number. Interesting, I think. Okay, there you have perhaps a not so gentle introduction to imaginary numbers. Not so much an introduction of how to use them, but two places where they occur. In amateur radio, anytime we're dealing with an alternating signal going through an inductor or a capacitor, we get the separation of current and voltage. And in order to express that mathematically, we need the domain of imaginary numbers. And any series like this is used all over, especially in higher power. So you get into Taylor series polynomials are very useful. You can fit almost any squiggle, curve fit it with a higher power Taylor series polynomial, and so these are real useful in business and science and engineering, and of course science and engineering are in the domain of physics, and so imaginary numbers occur in physics a lot. They're necessary. It's an unfortunate name for a very useful domain of numbers. All right, see you in the next video.